Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we'll be discussing on the rigid body dynamics in rotating frame, and this discussion will lead us to eventual study of complicated motions of spinning tops and gyroscopes, where we need several frames of reference to eventually understand these motions. So let us continue. So the topic of our discussion is rotating reference frame. Rotating reference frames, and we will be talking on the key concepts of velocity acceleration in moving frames and the effect of Earth's rotation. Okay, so we'll see that the second law, typically we have seen when we were looking at the Newtonian formulation, we were discussing the laws of motion, but they were all with respect to a fixed frame or the so-called inertial frames. Now we are now going to refer all our inertial frame dynamics as the dynamics in fixed frame, and the moving frame, which is the new frame we will introduce, is the so-called body fitted frame, in which the body, the frame moves with the body, right? So what I just said is that the second law has been related to only inertial frames so far, right? And in kinematics we are going to now look at both fixed frames and moving frames. We will look at both fixed frames and moving frames. And so the whole concept of a frame being fixed or a frame being moving is very arbitrary, because suppose we have a frame of reference in which, let's say, we look at Earth being the frame of reference, and suppose let's say a man or someone is moving or running, then we typically we expect that the Earth is the fixed frame of reference and the moving person is moving with respect to fixed frame. Now this whole description can be reversed. We could have a frame which is fixed on the moving object, and now that moving object is the fixed object in that body fitted frame, and the Earth is moving backward or in the reverse direction with respect to that moving frame. So this whole idea of fixed and moving is quite arbitrary. So what I just said is, so we have to fix frames as being fixed or moving, and then we proceed with our description. So in dynamics we have fixed frames, which is an inertial frames, where Newton's law applies. Okay, and then let us look at the dynamics with respect to fixed frame. Let us see what happens. So suppose we have a frame of reference. Let us call this frame of reference as our fixed frame. So let me call this frame as F. So this is F with these, let's say, the unit vectors as E1, E2 and E3. And now suppose we have a rigid body which we can visualize in this fixed frame. We could have another frame which is fitted in the body itself. We call this as the body fitted frame or the moving frame. So let me denote this body fitted frame as F prime. So from here onwards, all the primes are going to be denoted with the moving frames, and all the unprimed vectors and unprimed references will be referred to as the fixed frame quantities. So here we are. So now in this body fitted frame, this object will not have any translational velocity, but the object itself, in the body fitted frame, the object itself can rotate, right? So we are going to look at a special case where the object is only the object is only rotating with respect to the fixed frame, which means the body fitted frame itself is rotating and the object is fixed with respect to the body fitted frame. Okay, so let us say that this is omega, and now we have, let F be O, E1, E2, E3 be the fixed frame, and F be O, E1 prime, E2 prime, E3 prime, and this is the moving frame, right? And we have we are going to see that the rate of change of the velocity measured in the fixed frame is not equal to that in the moving frame. So this is typically the case. The rate of change in velocity in F is not equal to the rate of change in F prime. And now we can let us now start using some mathematical notations. Let us say we denote the velocities with u and try to measure the change in the velocities in the different frames. So what we have is, let us see this change in velocity u du dt in the fixed frame F, right? So say in a 3D space, it will have the following components. So this is u1 dot with E1 plus u2 dot with E2 plus u3 dot with E3, right? And similarly, du dot dt at F prime is going to be u1 dot E1 prime plus u2 dot E2 prime plus u3 dot E3 prime. And now, so these are the way we can determine the change in velocities or the change in this quantity u in the various frames. So let us say we denote the change or denote the quantities in the fixed frame as true values and in the moving frame as apparent values, right? So let us say the true, and let us denote the true and the apparent values, right? So the values of quantity measured in fixed frame is F, and the values of quantity measured in moving frame is F prime. And we have the fixed frame quantity are the true values and the moving frame quantities are the apparent values. Okay, so then we have the rate of change. So we expect that in the moving frame the basis vectors itself, they are they are changing with time, or the reference frame is the various coordinate vectors are also changing in time with respect to the inertial frame. So let us say we denote. So let me try and draw the diagram. So I have to keep referring to this diagram. So let me call this diagram as 1. So what we have is that we have a particle. So this is O prime, and we have, let's say, a particle P, and we are trying to observe the motion of this particle P. And we have this, that this is its position vector with respect to this frame is E prime. So this is the case, and with respect to the fixed frame O is E, right? And then we can try and also say that the distance between the reference, the origin of the two reference frames, let's say that is also, we denote it as the distance D, right? And of course the moving frame itself is changing with time, so we expect all these distances E prime and D to be changing with time. Let me, for the sake of consistency, denote the particle as E, not P. Okay, so then so what I just said is let E be any particle of the body B prime in which F prime is embedded, right? And we have that E and E prime be position vectors of E relative to O and O prime, right? So these are my position vectors of the particle E. And then now we expect that using the triangles inequality, we expect that E prime is going to be E plus D, right? So if we associate some arrows, then what we have is, from triangle inequality, we have that E is D plus E prime. Okay, so then what we have is, if we differentiate this equation, let me call this as equation 1. With time, we have that dE dt, of course, in the fixed frame of reference. In F is dE dd dt in F plus dE prime dt F, right? So this is also equal to, now the change in the origin. Let us say the origin is also shifting for the moving frame with respect to the fixed frame, and the rate of shift we denote it with the velocity v. So v plus dE prime dt of F, and that is what we have. Okay, so v now is the true velocity. So v is the true velocity of O, and this is the true velocity of the origin of the moving frame with respect to O, or this is the velocity of the frame F prime with respect to F, right? So then we can now denote this velocity as VE, as the true velocity, and we expect that the body, since we are talking about a body fitted frame, the body itself is not translating well. The only quantity that we expect to have within the body fitted frame is that this dE prime dt is going to be omega cross E prime, right? And so this is the this is the true rate of change. I think to the listeners, I just want to remind this that this formula comes from the fact we had seen few slides back that if we were to look at the motion of a body with respect to a fixed frame, then it all depends on the rotational velocity of the frame itself, provided that the body is not translating at this point. The frame is the body is not translating with respect to the moving frame, right? So this is all we have. So this is the true rate of change. Okay. So VE here is the true velocity here, and this is the true velocity of the object, of the body, and this dE dt is the true velocity of the frames, right? Relative frames. So now in particular, let us recap the important relation that we have just discovered. So in particular, the true rate of change of the basis vectors are E prime, E2 prime and E3 prime, and we have that we saw that in the moving frame this is nothing but if we were to look at the change, so dE prime dt, right? So all the basis vectors, the rate of change is given by omega cross Ej prime, right? So this is for all j, all the basis vectors. So this is an important recap from our discussion. Okay, so then if we were to now look at the relation now again, so our true velocity du dt with f is d dt with respect to j uj prime ej, right? So this is with respect to f. So this is also equal to summation uj dot ej prime plus summation uj ej prime dot, right? So these are what we have. So this is uj dot. So we have just distributed the derivative here. Now we can see that so these are all with respect to the frame f itself. So now using the relations, we see that this is also this quantity is also du dt in the frame f prime. Why? Because these quantities uj primes are just scalars, and now we are measuring these components with the basis vector uj prime, right? And then the other quantity is given by summation j uj omega cross ej prime. Okay. So then what we have is, so this is what we have, and then the relation becomes that du dt at f is du dt at f prime plus omega cross u, right? And our angular velocity omega, so omega is our angular velocity of the frame f prime with respect to f. Okay, so this is the vector relation. So angular velocity of f prime with respect to f. Okay. So then what we have is so this is let me call this formula as formula number 1, right? So we are measuring the true change in the velocity in the fixed frame. So now let us look at the velocity transformation formula. So another formula, the velocity transformation formula. So we have that R. So any position or any position of a particle in the fixed frame will be the position of the frame, the moving frame, plus the position in the moving frame of that particle. So that is what we have seen through the triangle inequality. Or if we differentiate with respect to time, so we have that dr dt at f is dd t at f plus dr prime dt at f, right? So now what we have is that this quantity, so this quantity is the velocity of the particle in the inertial frame. So let me denote it as small v, and this is the velocity of the frame itself. So this is our capital V. This is the same velocity which we had seen in the Formula 1, the relation for the true velocity. And then we also saw that this is the velocity of the particle in the moving frame. So the velocity of the particle, with respect to the inertial frame, the velocity of the particle in the moving frame could be a result of either translation or it could be rotation, right? So it could be either translation or rotation. So that is what we have. Okay, so then what we have is, suppose we were to write this entire, so this is what we have in, this is the formula that we have. Okay, so then let me call this formula 2 here. And now then we have one more result which I want to highlight here. So the third result is the so-called addition theorem for angular velocity. So this is very similar to the theorem that we saw for the true velocity or the result 1. So this result I will state it in the form of a theorem. So addition theorem for angular velocity. So suppose a rigid body in general motion has true angular velocity as omega, and apparent angular velocity as omega prime. Apparent angular velocity as omega prime. And then my omega is omega plus omega prime. So again, using the same idea that we saw in Formula 1. So the true angular velocity is the angular velocity of the frame plus the angular velocity in the frame, the moving frame, right? So we have, so this is very much analogous to our Formula 1, where we saw that VE was equal to V plus V prime E, right? So that is what we have. Okay, so then we have, let us look at an example. So the example says a circular cone with semi-angle 45 degrees, is fixed with its axis of symmetry. So this is a problem we would like to see. Axis of symmetry vertical, and its vertex O upwards. Okay. So the diagram is that we have that there is a cone with its vertex pointing upward, and then well, let me complete this statement. An identical cone also has its vertex fixed at O, and it rolls on the first cone so that its axis of symmetry precesses around the upward vertical. Okay, so then with angular velocity lambda, we need to find the angular velocity of the rolling cone. So find the angular velocity of the rolling cone. Okay, so this question is that we have a second cone which is rolling on top of the first cone here, right? And the first cone also is rotating about its vertical axis, and it's let us say this vertical axis is k hat or k bar, and the first cone's rotation angular velocity is lambda, right? And let us now also have denote another axis which is perpendicular to this k bar. Let us say this is the second axis n, which is perpendicular to k bar. Okay, so now, so what is happening is that to find this angular velocity of the second cone, so let me denote it by 1 and 2. So the second cone is also, first it is rotating, since there is a rolling contact, it is rotating with the first cone, right? But now, since this is a rolling contact, then we also expect that the second cone, not only it is rotating, but it is also rolling on the second cone. So there are two motions to be considered. One is the motion that we have to fix our frame of reference to simplify and look at this problem from a simplified perspective. So what we have is, so for the fixed cone, we see that, so f prime is a frame. So let us now, we have to fix our moving and our fixed frame. So our frame f prime, the moving frame is, let us keep this moving frame as the frame which is body fitted with the second cone, right? So frame with origin O and precessing with rolling cone, right? And then f is our fixed frame. So this is our fixed frame, which is, let me call this frame with the vertical axis k as our fixed frame f, right? So this is the f, right? Okay, so now what we have is that the second cone has an axis of symmetry about this vertical axis n, right? So in the rotating frame, so in frame f prime, what we see is that the frame with origin O, origin O prime, and well, we see that the frame with the contact, the two with origin is with origin O, right, is precessing. So it's precessing about this axis O comma n, right? So one cone is precessing about the axis k, and the other cone is precessing about the axis n, right? So now in frame f prime, so this is with angular velocity lambda, right? So what we have is that, so the angular velocity, so what we see is that the angular velocity, velocity of f prime, our moving frame with respect to f, is lambda of k, right? So the angular velocity with respect to f is lambda of k. So this is, so the moving frame itself is rotating about that first cone with the angular velocity lambda and direction k. Right now in frame f prime, so in f prime, what we see is that due to the rolling contact of the second cone, due to rolling contact between the cones, between two cones, the second cone must be rotating well, with now the angular velocity omega prime given by, now if we see the rotation is now clockwise, right? So if our fixed frame, the moving frame rotation is anti-clockwise, then the rolling rotation in the moving frame is clockwise, right? So we expect that in the moving frame our omega prime is minus lambda of n. Why minus? Because of the clockwise rotation. So which means now using our relation 3, that is from our theorem, that is the theorem that we had just stated here, the addition theorem for angular velocity. So from 3 we see that our net angular velocity is omega prime plus omega, right? And this is, so this is, we see that our omega is, so this capital omega is lambda of k and my omega prime is minus lambda of n, right? And if we were to find the magnitude of this angular velocity, we see that this is square root 2 lambda. Okay, so then now we can, I think I am all out of time for this module, and in the next module we will be looking at what happens to the acceleration in the moving frame. So thank you so far for listening.